So the next part is going to be inference on the parameters, like the one I talked about, to see how can we calculate the confidence interval on hypothesis. So now I trust you that when we say that we are looking for the inference, if we have like the equation for the confidence interval, we can calculate we are able to calculate the hypothesis testing as well, like do the process of the hypothesis testing as well, because they're the same things. Like you would need to just know the standard error of the situation, like, and the parameters when we say is the beta 0, beta 1, beta 2, all of these betas that we have. So for each of these beta, we want to find out the standard error. So that's the main thing. So for the whenever you hear about the inference on any parameters, not just beta, like if you are talking about those 4 cases that we had before, like mean, variance, those ones. Whenever you hear about inference on the parameter, look for a standard error. If you know what is the standard error of your situation, then you can write down your confidence interval as well as writing down your hypothesis test steps. So here for the inference on the parameter, the mean and the variance of the beta estimate, we would say that, okay, the expected value of the beta estimate is beta, like the true value of the beta. And the variance of the beta estimate is, I told you just in the previous section, that is x prime times x, and then -1 times sigma 2. And then that's for the whole like beta estimate. But when we say beta, is like we have beta 0, we have beta 1, we have beta 2. You can name it, you can start, it doesn't matter. Like if I have 3 betas, it means that in this matrix, this is going to be a matrix, right? So x prime x -1 times sigma 2 is going to give you a matrix. So I should know that in that matrix, where should I look for these variance for these betas? Look at here, I added, there is another thing as well, I believe. Let me just see. Yeah. So under the assumption of the normality of the error, we can say that the beta estimate, it has like normal distribution. The value that we are looking for is beta, and then x prime x -1. It's very similar to this one, but it's just that we can write it down like this as expected value, mean and variance, or you can write it down like this. You can write it in this form. Another thing that, make sure that at the end of this chapter, make sure to check the, I put some equation as reminders. So it's like that, whatever you hear here, all the equations on these chapters, I just try to have them like in a few pages back to each other, and then in a row. So you would have it like in front of you when you want to work with the tutorials. Over there, even you will see that. Whenever we are working with we want to find out the expected value and variance, we can write it down like this as well, like normal distribution, and then we would have the mean, and then I'm going to have the variance. The reason that I have I here is that it tells us that whenever you are looking for the, you're looking in the matrix and looking for like beta 1, it means that, okay, so you would go with the beta 1 in your, like, because we said that if you look at the example that we had, for beta we had a matrix, right? So we have a matrix of like let's say my matrix is a 1 column and 3 rows, because I have 3 parameters of beta. So what's going to happen is that you would need to consider, like if you're looking for beta 2, you would need to consider the second number in your row, and then like in the second row and the number that you would have, or the second element in your matrix. And at the same time, for variance, you would look at the diagonal, like the matrix that you have. So look at here, I have the, this is a review from the second year, but I have the matrix here, and then whatever you see here in the diagonal of it, that's your variance. That's like the, for example, if I'm looking for the variance of the, let's say beta 2, like if I start, let's say I start from the first beta that I have is beta 1, and then beta 2, beta 3. So like the diagonal, that the second element on your diagonal that you have, it's going to give you the variance of the beta 2. For beta 3, you're going to go to the main diagonal. And then here, this is my handwriting, so it's not that much good. But it's the variance of beta estimate. In fact, it's the variance, covariance of the beta estimate. When you hear it, you should read it like variance, covariance. Know that there is a covariance because we have more than like one beta here. And then the variance of the beta estimate is the equation that you can see on top as well. So when you make this equation, like expand this equation, x prime x time like -1, and then this sigma 2 is the same as MSE from the ANOVA table. When you generate this matrix, the diagonal values are variances. The off-diagonal elements, they're covariances, like covariance between beta 1 and beta 2. So, and because this is symmetric, so you can see that the covariance of the beta 1 and beta 2 is equal to the covariance of beta 2 and beta 1. Where does this covariance help us? It's the time that when you want to have comparison between these betas. In that case, this covariance is going to be very helpful because with the covariance, we are going to find out the standard error, right? So that's for the, so far for the variance covariance. Here is the confidence interval. So these are the equations that we have, and it's review again. So for the confidence interval for the individual parameter estimated, so it's a beta 1 plus minus. If your sigma 2 is known, it's like case 1. You would treat it with case 1. It rarely happens. You would work with the z table, and then you would have your standard error. Look at here, the standard error is sigma square root, like you have x prime x minus 1 I. Like this is the whole that you see here. This is gonna come from that matrix, right? And then you would have like a standard error. And then for if sigma 2 is unknown, you would use the x prime x minus 1 II, but you would use the s, like the same s that we had before, because you need the estimate of it. And then you would use the t for it to find out that like t, you would read it as like t half of the alpha n minus p. P is the number of parameter, like betas that you have, n is the total number of that. And here is a recall that you would have, like when we are having z of the beta, you can write it down like this. And here you can say MSE, it's equal to, like, we want to find out MSE, right? And this part comes from the ANOVA table. ANOVA table is very important in this course. So you would have your SSE, sum of the square of error. You can see sometimes they write it that residual sum of the square, like instead of SSE, RSS, or sometimes they write it down SS of the residuals. All of them are okay. I try to write down SSE, but you will see that even in our notes, sometimes I write down RSS as well, or even SSRES, because I want you to be familiar with it. They use error or residual, both are the same. Just know that in your ANOVA table, where can you look for your MSE? Because MSE, it's equal to the S2, right? Estimate for variance, and then is equal to SSE divided by n minus p. Okay. So here is the joint confidence region. And for joint confidence region, so far we have considered confidence interval on individual parameters. Like we would say that this is a confidence interval on beta 0, this is a confidence interval by beta 1. So we would have the standard error of each of those individual parameters, and we would have the confidence interval for them, right? This was done as if the other parameters and related regressors did not exist, but in reality, it's not like that. So we have some joint confidence region as well. It can be shown that the joint confidence region, or JCR, for all parameters is given by, we can have these two, we can use these two equations. And again, for sigma 2 known, sigma 2 unknown, sigma 2 known, it never happens. Like it's, probably you wouldn't see that for in the regressions. It's like that for, it's a special cases. It's like I've never seen that it happens, but it's like if it happens, we would go with the chi square. But the like the time that sigma 2 is unknown, That's the time that we would use F-table. Thankfully, we worked with F-table before. The only thing is that we need to write down this equation in a matrix form, and then we would need to go for each line. We would need to say that, okay, so that's less than this. Like for the when we want to write down the equations for the joint confidence region. So another part that we want to look at it is like the model predictions. We would say let W be a 1 times P row vector having the same format as a row of the X matrix. And then for a specific set of independent variables, we would say X null, or like the X of the, like, let's say X of the observation, is the Y for that point is equal to the W of that point times beta. So model predictions, we had something like the predicted interval when we were working on the different types of the interval in basic statistics. So we said that we have confidence interval, predicted interval, and tolerance interval. These are 3 intervals. This one is very similar to that. But here we are talking about the parameter, like of the beta. Over there in the second year, it's very similar, but over there we were working with the like 4 cases, like mean and sigma and those ones. So from this can obtain information about the mean response, the prediction of a single future measurement. So we would say the confidence interval on fitted value when we want to talk about the model predictions, it would be plus minus z of like whatever Y that you have estimate, plus minus some number from Z, and then from Z table, and then you would have your standard error, whatever it is. That's the confidence interval. The prediction interval, or PI, and a single future occurrence. Prediction interval most of the time is like this. So you have your, like, let's say you got samples of 50 samples from your population. So you want to know that what's going to happen, what would be the interval if I get the 51, like the next sample, what's going to happen? So that's the time that we use for the single future occurrence. And then it's very similar. The only thing is that for the standard error, when you want to write it down, you would say that whatever you had before, it's +1 under the root square. But the rest is very similar. So we would say that the first one, the confidence interval, is within, like inside the operating region that we have, but the prediction interval is always outside the operating region that we have. Okay, so these are some extension in least square regression. Least square regression, as we talked about that before, is like that you want to minimize the square of the residuals of your regression model. We would call it, when we read it, we just read it least square regression. I'm parting tops, okay. So the non-normality, so it's like that we would assume our epsilon, it has a normal distribution, and sigma with the expected value of 0 and the variance of sigma 2 needed for test of significance. Test of significance was it's the same like test of significance that we had before, and the confidence interval estimates are still blue. We would say best linear unbiased estimator if other assumptions hold. Transformation or other likelihood function can be used. We would say we have heterogeneous variance. We assume that the variance of epsilon is equal to I sigma 2. I is the identification, like is like I matrix, right? And then affects the minimum variance property of the parameter estimates. It's a loss of the precision. We have like correlated, these are just some remarks, I'm reading from them. So we have the correlated errors, the loss of parameter precision invalidates significance test. Like the correlated error occurs when data are collected in a time sequence. like pollutant emissions with time, biological studies, batch reactors. We have time series analysis and the generalized least square, so we can have the correlated errors on them on them. Then we have some, let's talk about outliers. Influential data points and outliers. The influential points have a greater impact on the least square results, yet all points are weighted equally. Outliers are values of the dependent variables that are inconsistent with the bulk of the data. Be careful, the outliers. We learned that in basic statistics in chapter, I believe, chapter 2, if I'm not wrong. Yeah, on chapter 2, that we can find out the outliers by with using box and whisker plots. Never remove the outliers just by looking by your by eyes. Don't trust it. So we can use the box and whisker plot method to remove the outliers. And here is another like modeling adequacies. Assume that the model is valid. The parameter estimators are unbiased only if the model is correct. And these are other things like we have about the collinearity. We can say when we have collinearity, we say solution is very unstable. A small change in the independent and dependent variable can cause drastic change in the parameter estimates. Variance of the parameter estimates involves nearly singularity situations that we would have, so become very large. You can think about this question: what else can we do to protect ourselves in practical cases? Just think about it. And then we have some problem with highly correlated parameter estimates as well. So usually means higher variance when the parameters are highly correlated and still we consider it. So it's gonna give us like higher variance, and we are hoping not to have higher variance because variance represents error, right? And it's like it means that parameters are less precisely estimated. Individual confidence interval are less meaningful. Like for testing for example, H null beta j is equal to 0 can lead to like we would have the conclusion in the presence of high covariance. There is more uncertainty about which independent variables are important. Correlations or covariances between parameter estimates become large if corresponding column of X matrix are highly non-orthogonal, or we would consider as ill conditioning. So when we are working with the variance and covariance matrix, our preference is that the covariance numbers wouldn't be that much large, right? Because it represents the correlation that we have. Area of the joint confidence region will be a smaller of orthogonal designs. And lengths of the individual confidence interval are much smaller for orthogonal designs. Orthogonal designs to be discussed in later. So when we are talking about the design of experiments, in those chapters, we're going to talk about this type of design, but it leads to the circular joint confidence region. But we are going to talk about this one. This part is like that. We will talk about it later. So you can look at this practice problem or tutorial. The file name is chapter 2, example 1, on linear regression model. And please review material from second year, whatever you think you will find it. Like I said that while we were working on the, like while I was talking in the chapter, I said that which part of the